Today we're going to look at the first attempts to explain the planetary motions, the rising and setting of the sun, the cycle of the phases of the moon, but more particularly, the extremely complex motions of the planets in the sky. We're going to take the perspective of the rise of the understanding of planetary motions in the Western world that comes to us from the work of the ancient Greeks. The motion of the celestial bodies visible to the naked eye are for the most part regular and repeatable. The stars rise in the east and set in the west every day. The sun rises and sets daily and moves eastward through the zodiac once a year along the path of the ecliptic. The moon rises and sets daily but moves eastward through the zodiac once through the course of the month, showing a sequence of phases that are very familiar to anyone who's walked outside at night and seen the moon in the sky. The motions of the planets, on the other hand, are not so simple. They're very much more complex, showing occasional retrograde motion. In general, planets seem to be well behaved. They rise in the east and set in the west along with everything else, and they move generally westward relative to the stars at varying speeds. But every now and then they will stop that general eastward motion, begin moving westward or retrograde, backwards, and then stop their westward motion and proceed moving eastward again. This is shown in this beautiful photograph of the motions of Mars during the appearance of Mars in 2005 and 2006, taken by the Turkish amateur astronomer Tunç Tetzel. You can see the general eastward motion of Mars eventually coming to a stop, moving retrograde, coming to a stop, and moving away. You'll notice something a little extra about this photograph. Mars is fainter, getting progressively brighter. That makes the image look bigger, becoming brightest when it is moving fastest retrograde, and then fading as it resumes its regular eastward motion. This is a clue as to what's going on. You can't just watch the motions. Sometimes you've got to watch what the planet is doing, how bright it appears to be with respect to the background stars. We'll come to that later. There are two ways to view the motions of the heaven. The most common sense way of viewing the motions in the heavens is geocentric or earth-centered. This is our perspective of the heavens. We stand, like Brutus here, upon the earth. We watch the sun rise in the east and set in the west. We watch the moon rise in the east and set in the west and move through its cycle of lunation. We watch the stars rise in the east and set in the west. And we watch the planets do the same. And we watch the planetary motions from this perspective where we appear to be standing at the center of the universe, the pinnacle of creation, the center of all things. It's not just egotism. It actually is how the universe looks to us if we aren't paying attention to certain subtleties. And so it's not surprising that the very first ideas about the shape of the universe, the ideas about the motions in the heavens, should be from this perspective of us standing at the middle, the earth at the center, and the rest of the heavens moving around us. It is how it looks, but appearances, as we're going to see, can be deceiving. So here we are in our geocentric system. The sun appears to rise in the east, set in the west, and move around us. Let's go now to ancient Greece. We're going to start our story of how we learned what the planetary motions were nearly 3,000 years ago in archaic Greece. When we think of Greece, most of us think of the main Greek mainland, Athens, Sparta, all of those places that center of Greece. But Greece was very much bigger than just what we now know as the modern country of Greece. The Greek people spread their way around the entire Mediterranean Sea and into the Black Sea, and between the years 800 and 480 BC, the Archaic period, had actually spanned the entire Mediterranean world, trade networks and colonies reaching as far as west as modern Spain, as far east as places that are now part of modern Russia, Turkey, and northern Africa. While we tend to think of Greek philosophy as centered at Athens, in reality, a lot of Greek thought occurred in the outlying areas. In particular, we're going to see that a lot of ancient Greek astronomy began not in Athens, but out in some of her eastern colonies on the western coast of what is now modern Turkey, at places like Miletus and Ephesus and the island of Rhodes. We begin with the very first philosopher recognizable from history, Thales of Miletus, who lived in the 6th century BC. Thales stands out from his contemporaries because he was the first recorded to us who began to seek to explain the phenomena of nature without resort to mythology. Before this, if you want an idea of how the heavens were viewed, you would look to the poets, you would look to the mythologists, you would look to the stories of Homer. Speaking in terms of gods and goddesses, or perhaps angels and demons, who knows? There are various ways of explaining the world in terms of magic and the supernatural. But Thales wasn't buying it. Thales was of the idea that you could explain the natural world without resort to the supernatural, without resort to gods and goddesses. As a result, he came into conflict with his society. He was actually accused at many times of impiety. He predicted eclipses and applied geometry and astronomy to surveying. He made the earliest studies of static electricity and wrote lost works on the solstices and equinoxes. What did Thales think of the model of the heavens? Sadly, we don't know. One of the problems of studying the origins of human thought is that much of what comes to us from the ancient world comes to us in fragments. There's a lot of history packed into 3,000 years, and not all of it was very kind to people or to the records that they left behind. But we do know of Thales' ideas and his practice of trying to explain nature without mythology, to use geometry and mathematics as a way of describing the motions, not just poetry and metaphor. These were an important start, and we know a lot about Thales' work, not because his works necessarily survive, but because of the descriptions of those works by one of his most famous students, Anaximander. Anaximander lived during the 6th century and was the first person that we know of in history to propose a geocentric model, at least a geocentric model that survived to come down to the present day, that we can ascribe it to him. Certainly, Anaximander, as a pupil of Thales, was probably building on an earlier tradition. Perhaps Thales himself was the first one to put forward a geocentric system. This is a carving, of course it's very fanciful, made many centuries later, of Thales, of Anaximander, in the National Museum in Rome. Thales and Anaximander would have described the world as flat. That certainly is the common sense perspective, even for those in the Greek world. Anaximander described to us a system in which the universe was spherical, at the center of which was a flat cylindrical earth fixed and unmoving at that center. Celestial bodies appear to move on different circles and lie at different distances from the earth. They projected onto this celestial sphere. He considered celestial bodies to be physical objects that were governed by knowable physical laws. This was a tremendous departure and probably reflects the deep influence of his teacher Thales. By describing the planets, the sun, the moon, and the stars as physical objects, he was pushing them into the same realm as the earth of physical objects, things that you can pick up, like rocks and trees. There's a story told about Anaximander that he said that the sun was nothing more than a burning rock. Well, to a people that believed in the mythological description of the sun as a celestial light carried along the chariot of Apollo, this was nothing short of heresy. And for a time he was accused of impiety and actually thrown out of the city. Well, shortly after he left, a meteor strike occurred. A hot rock falling from the space. Everyone ran out, saw, a hot rock appeared to have come out of the sky. Maybe it's a piece of the sun. We better get that Anaximander guy back. He might have been onto something. Well, we don't know exactly how the story went, but it was clear that there is a physical world that can be described as physical objects governed by physical laws. And Anaximander is certainly one of those who got the ball rolling on that line of thought. A century later, the great philosopher and mathematician Pythagoras, from whom we know the Pythagorean theorem, elaborated what comes down to us as the first quantitative geocentric model. The system of Anaximander was only described to us in words. It was Pythagoras who started the real application of a mathematical, quantitative description of the motions in the heavens. He described now a spherical Earth fixed at the center of the universe, with the planets and stars located physically on concentric crystalline spheres. The sizes and numbers of these spheres were in small number ratios, 2-to-1, 3-to-2, and so forth, and these spheres rubbed together in their motions. They were nested together as a physical system, and the vibrations of these motions in these exact number ratios created a harmonious music of the spheres. In addition to his studies of mathematics, Pythagoras studied musical harmonies. He considered the dulcet tones of whole number ratios of vibrations to be a sign of the underlying beauty of nature, and that beauty could be described in terms of number convinced him that using numbers, mathematics, and geometry to describe the world was to get at the underlying order beneath the rough appearances of the physical world. Pythagoras was a philosopher, however. He viewed things in terms of numbers, geometry, perhaps even aesthetics. And as a consequence, in many ways, while his model of the universe is the first quantitative geocentric system to come down to us, there are certain aspects of it that survived from his writings and those of his pupils that do not appeal to us. In many ways, they began to push the observations of the world to better match the ideals, these 2-to-1 whole number ratio, 2-to-1, 3-to-1, these harmonic ratios. Those were the ideals of perfection. In fact, the motions of the heavens do not follow such simple harmonic motions. Here was a case of falling in love with the beauty and symmetry of the system and trying to force nature into it, rather than trying to look at nature as it was and ask, how does it actually move, not how do we want it to move? So while Pythagoras made some advances, there were in there the seeds of the wrong approach. You have to pay attention to what the world says and not just simply force it into the beauty of your picture. This brings us forward to the classical period of Greece, which runs roughly from the 5th to the 3rd century BC. And now we're going to be looking at the Greek world centered around the Greek peninsula, Athens, Sparta, and the Greek islands of the Cyclades, heading out as far as places like Samos, Naxos, Andros, and other places. Eudoxus of Cnidus, who came from the islands around the year 400 BC, proposed a system of 27 nested crystalline spheres as a way of describing planetary motions. Eudoxus was a pupil of Plato and incorporated the Platonic ideals to explain planetary motions. He was a contemporary of his fellow pupil of Plato, Aristotle, and imbibed these ideas from Plato of the perfection of spheres and the idea of uniform circular motion. Platonic ideals saw the circle, the sphere, as the perfect geometric forms, the circle in the plane, the sphere in space, and uniform circular motions as expression of the perfection of the heavens. In the Platonic world, the universe was divided into the celestial realm of eternal unending perfection and the sublunar realm of the earth, the realm of change, death, and decay. So this twofold division of the heavens into the sublunar realm and the celestial realm was to be deeply influential for nearly 3,000 years. The idea that the motions in the heavens were somehow different and ruled by different rules than worked on the earth was highly influential, if somewhat misdirected, as we'll see. The system of Eudoxus has a certain logic to it. The outermost sphere of Eudoxus carries the stars. These rotate about an axis once per day, reproducing the rising of the stars in the east and the setting of the stars in the west. It is a continuous motion that is unchanging for all time. The next sphere is also rotating on an axis nested inside, but the axis of that sphere is tied to this outer stellar sphere and tilted by 23.5 degrees. This is the sphere of the sun. It is carried around the celestial sphere once per day by the motion of the outer starry sphere, but it too has its own independent motion, turning once per day around coming once a day around its axis to produce the rising and setting of the sun, and then slowly itself turning in the opposite direction once per year, producing the motion along the tilted path of the ecliptic through the course of a year. So the sun's motion in this system becomes a compound motion. The daily motion, as it's carried around by the sphere of the stars, and then its own individual motion being carried around the celestial sphere once per year against the background of stars along the tilted path of the ecliptic. The additional spheres are assigned to each of the planets in their turn. They're affixed to the sphere of the sun, and they have their own independent motion. The combined motion of all of these nested spheres produces the motions that we see in the heavens. The rising and setting in the east, because the whole machinery is carried by the outer sphere of the stars. And each of the more increasingly complex motions of the sun, moon, and the planets is by increasing nested spheres, each of them picking up the motions of the spheres outside of them, adding to the complexity. You build complexity by compounding what are individually very simple, perfect, uniform motions. It was this compound of smaller, uniform motions combining together to produce a sum that was more complex that is at the heart of the Platonic geocentric system. And separate, distinct from all of those, riding at the center, is the Earth. The elaboration of this system, the ultimate form of this system, comes to us from Eudoxus' fellow pupil Plato, the great philosopher Aristotle, who we've already met for his work on the shape of the Earth. Aristotle refined Eudoxus' system. He saw that the simple 27 crystalline spheres of Eudoxus were not sufficient to explain the tremendous complexity of the motions of the planets, and eventually elaborated a system that included a total of 55 crystalline spheres within spheres. The Earth is fixed and moving at the center because it is too big to rotate or to move itself. Aristotle here is applying physical properties to the Platonic ideal. Each of these spheres were themselves in a state of uniform circular motion, a constant speed along a circular path. This is a Platonic ideal of motion, and it only occurs in the celestial realm. It was a tremendous improvement over the system of Eudoxus, but it was not, in the end, perfect. It did not accurately predict the motions of the planets. It needed constant tweaking, constant adjustment, and even then, as it ran for a time, the predictions weren't very good. It worked for a little bit, but then it pretty much ran out, like a poorly built clockwork. This wasn't the only way to explain the motions in the heavens. There was another, alternative explanation that was possible. This is to flip the system, to say that, no, the Earth isn't at the center and the heavens are moving around us, but instead the Earth is but one of many planets and the sun is at the center. In this particular picture, now we say daily motion is due to the Earth rotating around its axis. The entire system then moves around the sun. We now have the daily motion just being the rotation of the Earth around its axis, and the annual motion is the revolution of the Earth around the sun. This is a sun-centered or heliocentric system. This attempts to explain the complexity of motions in the heavens as not due to the actual complexity of those motions, but that all of them are following simple motions around the sun, but that we are constrained to view those motions from the perspective of a similarly moving Earth. And it is the compound of their simple motions with our simple motions that together makes the complex whole. This is, in some ways, an equivalent way of looking at it, perhaps simpler, and some would argue a better physical description. The only heliocentric system we know of to survive to us from antiquity comes from Aristarchus of Samos from the 3rd century BC. We have already met Aristarchus for his measurements of the distances and sizes of the moon and the sun. It's very likely that Aristarchus was drawn to a heliocentric system by his measurements of the sizes of the sun and the moon, in particular the size of the sun. Aristarchus, coming after Aristotle, would have known the objections that Aristotle had made to the motion of the Earth. It's too big. Big objects are hard to move. Aristarchus's measurements found that the sun was very much bigger than the Earth. If it was an absurdity to Aristotle that the Earth might be in motion and therefore must be fixed and unmoving at the center of the universe, then wasn't it even a greater absurdity for the sun to be in motion, for the Earth to be fixed? Why should the smaller Earth be fixed and not the sun? This led Aristarchus to reverse the system, to set the sun, the biggest thing he knew of in the heavens, fixed and unmoving at the center of the universe, and set the Earth into motion. This cleared up to what to Aristarchus was a physical inconsistency with the geocentric model, as described by Eudoxus and Aristotle. Now, despite this, we don't know anything more about this system. In fact, we don't know what the Aristarchan system was in detail because the actual works of Aristarchus describing to it has not survived us from antiquity. What we do know of the Aristarchan system is from the writings of those who were actively dismissing it. For example, Hero of Alexandria wrote a long work describing why the Aristarchan system must be complete nonsense. But more importantly, there's a work by Archimedes called The Sand Reckoner, in which he describes the Aristarchan system only to say, this can't possibly work. It's that account in The Sand Reckoner that is to come down most vividly to us from antiquity and was to hold within it the spark of an idea that was to light nearly 2,000 years later in the head of Nicholas Copernicus. The Aristarchan heliocentric system goes a long way to explaining the planetary motions in a self-consistent way, but it never caught on because it ran up against this deeply held view, this deeply common sense view, that we are not in motion. The Earth is not rotating. The Earth is not moving around the sun, that we are fixed and unmoving at the center of the universe. This was a deeply held belief that was very difficult to root out. We're going to leave the heliocentric system aside for now because in antiquity, it didn't get very much further than Aristarchus. But we are going to look at now how did the ancients Greeks attempt to explain all the motions of the heaven with a purely geocentric system. The system of Aristotle wasn't working. Aristarchus knew that it wasn't working. So how did they make it work? How did something that wasn't working last for 2,000 years? That's what we're going to learn about in the second half of this lecture.